Right, so for today's topic about electrostatics, the learning outcomes, state and apply Coulomb's law to determine the force. Okay, so the force that we are referring to here is actually the electric force. Okay, of the point charges, can define and determine electric field of point charges and relate electric force and electric field, and also to determine the electric field in the conductor or around the conductor, and electric field between two parallel plates. Okay, so also electric potential energy of the charge and the system, electric potential or an equipotential line of the charge, work done, and to define electron volt. So quite a lot to cover in this topic. So I think most of you have played this before, okay? In your high school or in your primary school, when you drew a plastic ruler near to small pieces of paper, nothing will happen. Okay, but what if you do some magic on your plastic ruler, let's say by rubbing your ruler with a cloth, then only you drew your ruler near to the paper, and you will discover the paper, part of the paper will stick on your plastic ruler. Okay, so is this because of magic? I think most of you know, right? This is because of electrostatic. So what happened here is when you rub your plastic ruler with the cloth, okay, some of the charges, okay, let's say this is your cloth. When you rub them, okay, some of the charge has gone to your cloth. So let's say positive charge has jumped over to your cloth. So left only mostly negative charge on your ruler. So now your ruler is charged. By drawing near the ruler to the small pieces of paper, okay, the paper you have neutral charge, right? The balance amount of positive and negative charges. But when you draw the negatively charged ruler near to the small pieces of paper, what happens is the positive charge of the paper will be attracted to the plastic ruler, while the negative charge in your small pieces of paper will stay away from your ruler. So that's why the paper will somehow be attracted to the ruler. And this phenomenon has been widely explained by Coulomb's law, right? So it's something that you have already known, saying that if two charges, they have the same sign, they will experience repulsive force. So if the two charges have different signs, they will experience attractive force. Okay, so let's say if you have two positive charge, they tend to repel against each other. But if you have one positive and one negative, opposite charges attract, so they will be attracted. And it further says about the strength of the electric force. So the strength of the electric force is directly proportional to the product of two charges. Okay, so it mentioned only about the interaction between two charges. So which means your F is directly proportional to the charge which is given by Q1 and Q2. So let's say if this is Q1 and this is Q2. So how strong is the force between them depending on the charge they contain by your Q1 and Q2. And electric force is also inversely proportional with what? With the square of the distance. So let's say if the distance between your Q1, Q2 is R, then the force is inversely proportional with the square of the distance. So 1 over R squared. So electric force, since this is a force, so the symbol is given as F, and the unit for force is Newton. Okay, same as what you have learned previously. Alright, so to find the magnitude of electric force, alright, so you have already know, right, from Coulomb's law, F is directly proportional with the charge in Q1 and Q2, but inversely proportional with the square of the distance. So if you want to put an equal in between, is equals to a constant times Q1, Q2 divided by R squared. Okay, so this constant is what we call as Coulomb's constant, and it's given by 9 times 10 to the power of 9. And if you look at the unit here, they are all in SI unit. Alright, so the formula for electric force is equal to K Q1 Q2 divided by R squared, whereby the Q is the charge of the particles that involve, right? And the SI unit for charge is in Coulomb. R is the distance between the two charges and is in meter. Alright, so look at the example here. You have two positive charge standing side by side next to each other. So according to Coulomb's law, same charges repel. So the force that experienced by Q1 because of Q2 is now moving away from Q2. That's why this is your force. And looking at second example, when you have two different charges, one positive and one negative, according to Coulomb's law, opposite charges attracts. So the charge on your Q1 is now moving, experience a force which is moving towards your Q3. Alright? And if you recall what you have learned in semester 1, force is a vector. So when it is vector, there are two things that you need to take into account. What are they? So they are, the first one, you have to consider the direction, and second one, you have to consider the magnitude. So that's why in force, okay, we draw the direction. So in order to solve the problems for electric force, okay, I've come up with 3 important steps. Recalling force is a vector, right? So always the first steps to find the direction. Direction comes first, then followed by magnitude, then only combine them to find the net force. Alright? So let's look at the example. Okay, we have 3 charges, Q1, Q2, and 1 charge with 2 nanocoulomb is positioned at O. So you have to find the electric force experienced by this positive charge at position O. So now let's follow the steps to look for the electric force. Okay, step number 1, look for direction. Alright, so Coulomb's law states if 2 charges have the same sign, they will repel. If they have the opposite signs, they will attract. So now let's look at Q1 and let's assign this one as our QO. Look at Q1 and QO first. Okay, so between Q1 and QO, both of them have positive charge. So they will repel against each other. Alright, so taking QO as our reference charge, the force that acting on QO because of Q1 is now moving away from Q1. So this is the directions of your F1O. And now looking at Q2 and QO. Q2 negative charge, QO positive charge. They are in opposite signs. So the force that acting on QO is attractive to Q2. Hence, the direction of force will be moving towards your Q2. So this is the directions of your F2O. So here, done with our first steps. Now we're moving on to second step. Look for the magnitude. So the formula for electric force equals to K, the 2 charges, force between Q1 and QO. So KQ1 times KQO divide by the distance between 1O square. Plug in the value. That gives you 6.75 times 10 to the power of negative 5 Newton. Alright, now proceed to look for F2O. So equals to KQ2 QO divided by R between Q2 and QO square. So plug in the value. Okay, so look at this Q2. Okay, we do not put in any positive and negative sign in front of Q2. Why? Because this is a vector. So for vector, remember, your positive or negative sign only shows the direction. So it does not take into account into your calculations, right? So even though Q2 is a negative charge, we do not put any sign in front. But we will look for the directions. That's why we have already drawn the direction in our first steps. And now look at 0.05. Where does this 0.05 comes from? Okay, if you look at the diagram, this is a right angle triangle, correct? So 3 centimeter, 4 centimeter. By your Pythagoras theorem, this is 5 centimeter. Okay? So your F2O is 5.676 times 10 to the power of negative 5 Newton. So, done for our second step. Now we have to look for our net force. If you recall what you have learned in semester 1, your vector, your force is a vector, right? So, when it comes to vector, we have to look for the directions. Okay, so if they are going into the same directions, we add together. If they are going into opposite direction, we have to minus. And now if we have two-dimensional, okay, so in this case, my F1O and my F2O, they are not falling on the same line, correct? So we cannot straight away plus or minus. But what we have to do? Yes, we have to resolve to X and Y component, which is kind of like a bit of tedious, but if you are familiar with it, you won't feel too bad about it. Alright, so draw the table to resolve to X component. And Y component. F1 and F2. So looking at your F1, okay, your F1 is all on the X component. So F1 is equals to 6.75 times 10 to the power of negative 5, and the direction is going to the right. Y component of your F1 is equals to 0. Now the tedious part comes. Okay, we have to resolve F2 to both the X and Y component, right? So taking this right angle triangle, okay, so this is our theta, right? So resolving to X component is this component. So it is actually a cos theta, F2 or cos theta as your Y component. So F2O is 5.676 times 10 to the power of negative 5. And your cos theta, if you look at the diagram, cos, this side is 4, so this side will be your 5, right? So which is 4 over 5. And that gives you 4.61 times 10 to the power of negative 5. And moving towards the left. For the Y component, F, this is the Y component, right? So look at the trigonometry is sinus. So F2O sine theta. So 5.76 times 10 to the power of negative 5. Sine theta is 3 over 5. And that gives you 3.46 times 10 to the power of negative 5, moving downwards. Alright, so now we have to combine the total X and Y component, right? So total X component. So in vector, we have to take one direction as positive and the other direction will be your negative. So let's say we take going to the right as positive. Alright, so you have 6.75 times 10 to the power of negative 5 minus 4.61 times 10 to the power of negative 5. And that will give you 2.14 times 10 to the power of negative 5. So since it is a positive, so the direction's moving towards the right. So same go for your total y. So by taking, going up as positive, so you combine your Fy, you have negative 3.46 times 10 to the power of negative 5, and it's moving downwards. So if you draw them into diagram, you will get your total S component 2.14 times 10 to the power of negative 5, and your total Y component, which is 3.46 times 10 to the power of negative 5. So your net force or your resultant force will be in this direction. Alright, which can actually be solved by Pythagoras theorem, moving this side to this side. This is a right angle triangle. So last step to solve the net force. So equals to your total Fx square plus your Fy square and root square. So you get 4.06 times 10 to the power of negative 5 Newton. Right? So that solves our third step. Okay. So electric field. Electric field is related with electric force. Okay? Because electric field is something that is released by any charged particle. So as long as if the particle is charged, then around it, it will have its aura. Okay, we can consider electric field as the aura of a charged particle. So because of this aura or because of this field, okay, any charge that go nearer it. So let's say if you have a positive charge, okay, so we know around this positive charge, you have all the aura. Okay, so because of this aura or because of this field, any other particle, a charged particle, if you place near it, this particle will experience an electric force. Alright, so this is what it means by the first sentence. Okay, it's the region around a charged particle with which, okay, when an object is put nearer to it, a force will be exerted on the charge. Okay, so it is also equivalent to the force that felt by the test charge, let's say, is this charge Q2. This is Q1. Okay, so electric field is also equals to the force that felt by this charge. So I can say is the force experienced by charge 2 because of charge 1 divide by the magnitude of the test charge, divide by your Q2. Right? And the last one means electric field line is always pointing outward from positive charge but inward for negative charge. This is a very important concept that you need to know for electric field. Okay? Positive charge, your field is always going upwards because you are so positive that you can give away so many things. And if you are a negative charge, then you are always receiving from the others. Right? So for electric field, we give them a symbol of E, and the unit is Newton per Coulomb. So looking back at this formula, E equals to F over Q, right? If you still remember, F is in Newton, Q is in Coulomb. That's why it maps out your electric field unit in Newton per Coulomb. Okay, so if we look at the example here, electric field for positive charge is always going outwards from the positive charge. So the formula of electric field is given that is referring to one charge only, right? So let's say we have a positive charge here, and you are asked to look for the electric field at point P. So since electric field is always going outward from positive charge, so at this point P, that will be the directions of your electric field. So the directions of electric field due to Q1 at point P is going diagonally upwards. And the formula is given by K times Q1, which is the charge on Q1, divided by the distance between your charge Q1 and your position P. And the distance, remember to square the distance, right? So again, electric field, same as electric force, is a vector. So when it comes to vector, you have to remember what? Yeah, the first thing is direction. And the second thing is your magnitude. Okay, so same for your negative charge. So because electric field for negative charge is always going inward, so at this point P, your directions of the field is going diagonally downwards. So the steps for solving problems with electric field is the same as electric force. Start with direction, because it is a vector, followed by the magnitude, and lastly, only you look for the net field. So it's somehow similar as your example in electric force. But now, the difference is we remove the charge on position O. Alright? So, find the electric field at point O. Okay, so the first step, start with the direction first. Okay, so directions. Now we look at Q1 first. Electric field at point O, because of Q1, is moving away from positive charge, because electric field from positive charge is always going outwards, right? So that will be your E1. And looking at Q2 and position O, electric field at position O due to Q2 is moving towards your Q2, because Q2 is a negative charge. So settle our step 1. Now we look for our step 2. Look for the magnitude. So E1 equals to K Q1 divided by R1 square. So 9.0 times 10 to the power of 9 times with your Q1, which is 6.0 nanocoulomb, divided by the distance 0.04 square. You get 33.75 to the power of 3. And E2 is K Q2 divided by R square. So 9.0 times 10 to the power of 9. Okay, again, in this case, we do not put the negative sign because this is a vector. Okay, so the distance is 5 centimeter. So you get 28.80 times 10 to the power 3. Okay, settle for second steps. Now, look for the net field again, because this is a vector and they are not on the same line. Resolving to x and y component is needed. Alright, so draw your table. X component, y component, E1 and E2. So your E1 is only x component. So just copy down, which is equivalent to 33.75 times 10 to the power of 3, and is moving towards the right. And no y component for E1. And now for E2, again, this is a right angle triangle. So taking this one as our theta, so resolving to x and y component. This is the x component, which is a cos. So it's equals to E2 cos theta. E2 is 28.8. Cos theta is correct. Like just now, it's 4/5. So you get 23.04 times 10 to the power of 3. What is the direction? Moving towards the left. So y component will be E2 sine theta, right? Looking at the diagram, this is your y component, which is here. So it's a sine. So equals to 28.8 sine theta, which is 3/5. And that will gives you 17.28 times 10 to the power of 3, and the direction is moving downwards. Okay, now find the total x component. So your EX will be, so again, going to the right as positive. So 33.75 times 10 to the power of 3 minus 23.04 times 10 to the power of 3 gives you 10.71. And because this is positive, so it is moving to the right. So y component taking upwards as positive. You get 17.28 times 10 to the power of 3, because this is the only one component that you have. So because this is Pythagoras theorem, so look for your E net. So you have 20.3 times 10 to the power of 3 nano per coulomb. Okay. So next, part B, subsequently find the electric force experienced by a positive charge. So isn't it similar to the previous questions, where you have a +2 nanocoulomb positive charge position at O. Okay, recall back to here. Since E equals to F divided by Q, so rearrange, we can have electric force equals to Q times E, in which this Q, let's say this is the position O, okay, position O, in which this is the electric field at position O, and this is the charge placed at position O. Correct. So if we look at this example, okay, if we want to find the electric force experienced by this charge, then it will be equivalent to the charge of this 2 nanocoulomb times with the electric field at this position. So we have already had our electric field, which is 20.3. So we can find the force. So it's equals to Q times E, whereby the Q is 2 nanocoulombs times E, 20.3 times 10 to the power of 3. So that will give us 4.06 times 10 to the power of negative 5 Newton. Isn't it the same as your previous example? So we can actually solve them with different way, depends on what information that you have. Alright, so by knowing the pattern of electric field, we can get different kind of pattern with different types of charge orientation. Right? So it's always follow the rule. Positive charge, the electric field is going outwards and going inward into your negative charge. Okay, so if you have two positive charge sitting side by side, so because the positive charge is always going outward from the positive charge, so there will be a vacuum here whereby your electric field is equal to 0. So if you have a conductor or a parallel plates, so all the field will just touch on the surface like this one. Alright? Now let's look at the electric field in a conductor. So in a conductor, we have not only one positive charge or one negative charge. We will have a lot of positive and negative charge scattered around in a neutral conductor. But what if this conductor is being charged? Okay, so let's say if it is positively charged. When we say something is charged, it means the net positive charge is more than the negative charge. So let's say it is positively charged. So when it is positively charged in the conductor, what happens is, according to Coulomb's law, they are all with the same charge, right? So same charges repel. So what happens is all the charge, they will try to separate as far as possible. They don't want to gather together at the middle. And in order to separate as far as possible, they will just go to the surface, right? To distance from each other. So what happens is, when all the charge has gathered on the surface, what left in the center? What left in the center? So at the center here, there is nothing left, right? So when there is nothing left, your electric field is equal to 0. So electric field inside a conductor is 0. Alright? And because all the charge has gathered on the surface, so outside the conductor, this conductor looks like a charged particle, like a positively charged particle. So that's why outside the conductor, you will have electric field. And since this is positively charged, so your electric field is moving upwards and is always perpendicular to the surface of the conductor. Okay? So any excess charge will reside entirely on the surface of the conductor. So all the charge will just fall on the surface of the conductor. They will never go into the center of the conductor, right? So because of this one, okay, this is what we call as Faraday's cage phenomenon. So Faraday cage is when you have a conductor being placed in an electric field. So let's say this is positive and this is negative side. So any electric field coming out from the positive side will be neutralized by the negative charge in your conductor. And any electric field contributed by this negative charge will also be balanced off by your positive charge in your conductor. So what left in the between here is nothing. Okay, so it's a zero electric field. So actually this one is very useful, and somehow it actually helps to protect us from a lot of hazards. Okay, so let's say during rainy day, thunderstorm rainy day. Okay, so if you stay in your house, okay, and if the thunder strike on your house, the human that stay inside, will you be affected? No, right? Because of the Faraday cage, all the current will just go down outside of your house. So people that stay inside will be safe and sound. Same goes to if you are driving during the rainy day. Okay, so if you're sitting inside, right? If the thunder strike your car, you will be safe inside here. Why? Because the car serves as a Faraday cage, which has neutralized all the current outside your car. So the people that sitting inside will be safe, right? So let's move on to the electric field between two parallel plates. So again, if you have two parallel plates, one plate positively charged and the other one negatively charged, so the electric field only moving from positive charge, moving out from positive charge and going into your negative charge. And the electric field in between the parallel plates, any point inside in between here is uniform, which means it's the same and is represented by this one, V over D, where your V is the potential difference between two plates, and the unit is in volts. Potential difference means voltage difference, or we can say it's actually the voltage, right? And D is the distance between the two plates, and it is in meter. So from here, you can get another unit for your electric field. V, since it is in voltage, D is in meter, so the unit for your electric field can be written as voltage per meter. We will come back to the example later. Yeah? Alright, so anything with force will do work, agree? So anything that do work will have energy. So same for the charge, okay? We have electric force, so we will have electric potential energy as well, okay? So there are two types of electric potential energy. One is potential energy of a charge, and the other one is potential energy of the system. Okay, so if it is referring to a charge, then it's only referring to the interaction between that particular charge with the surrounding charge. Alright? And if it is referring to the system, then it is referring to the all types of interaction within the system itself. So we will look at the difference between them at the example later. Okay, so electric potential energy is in the symbol of U, and since it is energy, so the unit is in joule. Okay, the good things about potential energy, okay, if you can recall, energy is a scalar or a vector. Energy is a scalar. Okay, so when it comes to scalar, you have only magnitude. It's a good news for you because you don't have to look at the direction. So no direction means no x and y component. Okay? So for electric potential energy, the formula is given by K times Q1, Q2 divided by R. Okay, so again, it refers to the interaction between the two charges, which is Q1 and Q2. All right, so the potential energy of your Q1 because of Q2 is given by K Coulomb constant times the charge in Q1 and Q2 divided by R, which is the distance between your Q1 and Q2. So look at here. Okay, we put, for this time, the charge on Q1 and Q2, we use capital Q to represent them because for this application, you must include the positive and negative sign. Okay, so because for scalar quantity, we do not take account into the direction. So we have to count the sign. So I put 3 stars here, means that it's very important. You must include the positive and negative sign. Okay, so now let's try the example. Okay, same orientation as your previous example. So now you have to look for the potential energy of this charge that placed at position O. So let's denote it as QO. Okay? So again, still remember, for potential energy is given by K, Q1, Q2 divided by R, correct? So now we look at the interaction between Q1 and QO first. So U1O is equals to K Q1 QO divided by R 1O. Plug in the value 9 times 10 to the power of 9. Q1 6.0 nano. QO 2.0 nano divided by distance 0.04. Okay? Next, look at the interaction between Q2 and QO. So it's equals to K Q2 QO divided by R2O. So for this one, you have to include the negative sign. Okay, so the energy that experienced by your QO, okay, because O is only interacting with Q1 and Q2, so it's equals to potential energy between 1 and O plus potential energy between 2 and O. So that will give you negative 1.8 times 10 to the power of negative 7 joule. So that is for the point charge of QO only. So how about the potential energy of the system? Okay, so now when we talk about system, we have to look at all the possible interactions. So what are the interactions that you can have? We can have the interaction between Q1 and QO just now, and Q2 and QO. What else you have? Yes, Q1 and Q2. Okay, so there are 3 combinations. All right, so write down all of them. Potential energy of the system is equals to potential energy between 1O, potential energy between 2O, and potential energy between 1 and 2. So you write down Q1 QO divided by the distance between 1O. Okay, Q2 QO divided by distance between 2O. And KQ1 Q2 divided by the distance between 1 and 2. Right? So write down all of them. And that will give you negative 14.58 times 10 to the power of negative 5 joule. Right? So that is the difference between system and point charge. Now look at potential. Right? So for potential, there are 3 terms you have to know. Okay, so what is actually potential? Potential is something like voltage. So something that is charged, you have voltage. So that voltage will eventually cause any charge that's sitting next to it to experience an energy. Okay, so potential is similar like electric field. It's also a kind of the aura measurement of the charged particle. Okay, so potential is equivalent to potential energy for unit charge. U per Q. Potential is given as the symbol of V. And it's the work per unit of charge required to move a charge from a reference point to a specific point. Okay, it's also equals to the work done divided by Q also. Alright? Okay, so potential difference, when we look at the word difference, means there is a point at initial point and there is another one which is the final point. So for this one, which means is the final potential minus the initial potential. Right? So potential difference is always used to find the work done. So let's say if we have a charge here. So any charge around it, they will release the aura, which is the potential. Okay? So if I want to bring another charge to this position, okay, we need to do some work in order to bring this charge to that position, okay, because of the potential, right? And the last terms here is equipotential. Equi comes from the word equal, okay? So equal potential means you have the same potential. So if this is an equipotential surface, so which means the potential on this surface will always be the same. So let's say if this is your equipotential line, which means the potential here will be equivalent to the potential here and will be equivalent to the potential here, right? And on equipotential surface, the potential difference is always 0 because they are the same. And the equipotential surface must be perpendicular to the electric field line. Okay, so we will look at this one. And the unit for potential is in volts. As I have said before, potential, you just treat it as voltage. So the unit is volts. So if you still remember, electric field lines for any charge, for positive charge, is going radially outward, right? And your potential is always follow the shape of your conductor or the shape of your charge. So that's why at any point also, you will definitely get 90 degrees between your equipotential lines and your electric field lines. Okay? So how to calculate potential? Potential is given by KQ divided by R. So let's say if I want to find a potential at point P, and like what I said just now, okay, any charged particle has potential around it. So if let's say this is the point where I need to check the potential, so it will be equals to Coulomb's law, Coulomb's constant times Q1, which is this charge that contribute to the potential at this point, divided by R1, which is equivalent to the distance between your point P and Q1. Alright, so same goes to your negative charge. Okay, potential, how to find the potential is the same. Okay, and because it's a potential is also a scalar property, so you do not need to look for a direction, but remember to include the sign, positive and negative sign. Alright? So it is similar as electric field and electric force, but it's just that for potential and potential energy, it's a scalar, and the formula is a bit different by the R. Okay, your R does not has the square. Okay, now we try the example. So find the electric potential at point O. Okay, so at this point, the potential at point O is contributed by Q1 and Q2, correct? So potential at point O is equals to your potential that contributed by Q1 plus potential contributed by Q2. So KQ1 divided by R1 plus KQ2 divided by R2. So for this one, remember the negative sign. And that will give you your potential at that point is negative 90 volts. So subsequently find the work done to move a charge which is 2.0 nanocoulomb from infinity to point O. Right, now I'm moving a positive charge from infinity to here. Alright, so if we refer back to our previous formula, V equals to work done divided by Q, correct? So rearranging this one, we'll get W equals to Q's time change in V, okay? Because you need to have different in potential, only you can do work. So W equals to Q times change in V, which is V final minus V initial. So 2.0 nano times 90 will give you negative 1.8 times 10 to the power of negative 7 joule. So this is how we can find the work done. Right? Last part is the electron volt. So by knowing that voltage will cause the charge to do work, okay, so this is how we have come up with another measurement of the energy. Okay, so under a potential difference, so let's say if we have two terminals, one positive charge and one negative charge, and when you measure by the voltage, it gives you one voltage difference. Okay, so under one voltage difference, okay, if we release an electron here, the energy that used by this electron to accelerate from negative terminal to positive terminal under one voltage difference is called as 1 electron volt. And 1 electron volt is equivalent to 1.6 times 10 to the power of negative 19. Alright? It's actually a measurement of energy. Okay? So now we back to this example. So electron gun, okay, has two parallel plates separated by 4 centimeter, and it gives the electron, okay, one electron only 25.0 kilo electron volt of energy. So you are asked to find what is the electric field strength. Remember, for parallel plates, electric field is given by voltage divided by distance. Okay, so we have the distance, we need to find the voltage. So given here, okay, the two plates has given the electron with 25 kilo electron volts of energy. So how does energy related with voltage? Voltage is equals to energy divided by the charge, correct? So your energy is 25 kilo electron volt. Have to convert to joule. So 1 electron volt equals to 1.6 times 10 to the power of negative 19 joule. Divide by Q. Your Q is the charge of electron, which is 1.6 times 10 to the power of negative 19. So 1.6 times 10 to the power of negative 19. So your voltage is equivalent to 25.0 kilovolts. So your plugging back to your electric field, distance convert to meter, you get 325 kilo. Not 300, sorry. You get 625 kilo, and is in voltage per meter. And subsequently, you insert a plastic with a charge 0.5 microcoulomb. Okay, so what happened is between the two parallel plates, okay, you put another thing inside with 0.5 microcoulomb, and you have to find the force. Okay, so do you still remember the electric field between the parallel plates are uniform, which is represented by this one, right? Okay, so now we have know the electric field, and we know the charge that is being put inside the electric field, so we can look for the electric force. So part B, electric force equals to Q times E. So the Q is 0.500 micro times with the field, which is 625 K. You get 0.31 Newton. Okay, the summary of this topic, okay, referring to the learning outcome, state and apply Coulomb's law to determine the force on a system of point charge. So, electric force equals to K Q1 Q2 divided by R squared. Alright, so electric force is a vector. So how do we determine the direction? Yeah, same charges repel, but opposite charges attracts. Determine and define electric field. So electric field is E equals to KQ divided by R squared. So it's again vector. So how do we determine the direction? Electric field for positive charge is always going radially outwards. Negative charge going radially inward. Alright? So how to relate force and field? Force is equals to Q times E. Electric field in conductor. So electric field inside the conductor is always equals to 0, right? So outside around the conductor, then it will be equivalent to this one. Electric field between two parallel plates. So E equals to voltage divided by distance. Okay. Now move on to potential energy. So potential energy equals to K Q1 Q2 divided by R. So it's a scalar. So you have to include the positive and negative sign. Potential and equipotential. So potential is equals to KQ over R. Right? Work done. So work done equals to Q times change of B. So change of B refers to final potential minus initial potential. And lastly, electron volt. So 1 electron volt equals to 1.6 times 10 to the power of negative 19 joule.